So now we're moving to topic 3, lesson 2, plate tectonics and Earth's surface, which are covered on pages 108 through 117 in your textbook. All right, so plate tectonics and Earth's surface, we're going to go ahead and do the connect it. So the first thing we're supposed to do is identify where the Himalayan mountains are and circle them in our textbook. And your image should look something like this, and then your circle should go about there. Now, scientists are measuring Mount Everest to determine whether its height has changed. Why would the Himalayas be getting taller? And if India keeps moving into Asia, the mountains could keep crumbling and growing in height. And that has to do with the plates and how they're moving, which we will discuss in this section. So the theory of plate tectonics. With observations of many geologists in the 1950s and 1960s, particularly of the features of the ocean floor, the ideas behind continental drift re-emerged as the theory of plate tectonics. Tectonic refers to Earth's crust and to the large-scale processes that occur within it. The theory of plate tectonics suggests that the crust and top of the mantle are broken into distinct plates that fit together like a puzzle. All right, convection drives plate motions. So the tectonic plates move because they are part of convection currents in the mantle. Remember that warm things rise while cold things sink. Convection currents work exactly the same way. Convection occurs in the mantle, where solid rock flows in slow-moving currents. These currents are responsible for moving the contents great distances across Earth's surface. So here we have image or figure 3, oceanic continental crust. The very dense crust of the ocean floor is oceanic crust. Crust that is less dense can be thick enough that it's above sea level. Continental crust gets its name from the fact that surfaces of continents are mostly above sea level. So we're going to use the directions in which the convection currents are moving in the figure to draw in arrows indicating the direction of the oceanic plates. So here are our plates right here and here. And the convection currents, the plates are going to move with those. So this one's going to move this way and continue going that way, while this one over here is going to move the opposite direction away from the other because of the direction that the convection currents are going. Wow, that arrow did not stay on. I got distracted there. So sorry. Wow, that doesn't even look like an arrow. Anyways, so the convection currents, because they're cycling around the tectonic plate, is going to move in the direction that it's going. And that's the oceanic plate. Types of crust. So plates consist of one or two types of crust. You have the oceanic crust, which is the dense type of crust that is found at the bottom of the ocean. And then you have the continental crust, which is less dense and is almost always thicker. As a result, the surfaces of continents are above sea level. Plate motions over time. Scientists use satellites to measure plate motions precisely. The plates move very slowly, about 1 to 10 centimeters per year. Because the plates have been moving for billions of years, they have moved great distances. All right, so here we have figure 4, 200 million years of plate motions. It has taken the continents about 200 million years to move to their present locations since the breakup of Pangaea. So we're going to label the land masses from 115 million years ago with the present day names of land masses as shown on the Earth Today map. All right, so here we have North America. And then Europe is going to be here. Asia is going to be here. We're going to have Africa right here. This here is going to be South America. And then we're going to have Antarctica down here. And Australia here. Hopefully my U and N look different enough. Also, there's the plate tectonics video, which I will post in Google Classroom. Plate motions over time. Over time, the movement of Earth's plates has greatly changed the locations of the continents and the size and shape of the ocean basins. Before Pangaea existed, over billions of years, other supercontinents had formed and split apart. When might the continents we know today form a new supercontinent? And we could estimate that in 200 to 300 million years from now, we could potentially have a new supercontinent. Tectonic plates in the Ring of Fire. The theory of plate tectonics predicts that earthquakes and volcanoes should occur at plate boundaries, and that some landforms, such as mountain ranges, should mark the plate boundaries. Using this information, we're going to fill in the questions on page 112. Okay, so on 112, there's the Model It Ring of Fire. Because the region around the Pacific Ocean is prone to volcanic activity and earthquakes, it is known as the Ring of Fire. Why do so many volcanoes seem to occur on coastlines of the Pacific Ocean? And volcanoes often occur along plate boundaries, and there are many plate boundaries along the Pacific coastline. So, now, according to the theory of plate tectonics, how do the locations of volcanoes compare with plate boundaries? On figure 5, draw the edges of the different plates, including the Pacific plate. Use figure 6 to help you. So on page 113, you guys have an image that will help you draw these beautiful lines, but I'm going to wing it, and I'm sure it's not going to be great, but here we go. All right, there's one. Actually, that's a lie. This one comes up around here. All right, so on and so forth. So there are more, and you guys can continue drawing those in your book, but it should look something similar to this. I would think that you guys could probably draw better considering you have a pencil and paper and are not using a tiny keypad on the laptop. So describe how the symbols on the map guide your mark up of the map. So I use the locations of volcanoes to help determine the edges of the plate, which is true because it follows along the volcanic lines. Plate boundaries. There are 3 ways in which plates move. There's the divergent boundary, which are when plates move apart or away from each other. And this makes mid-ocean ridges and valleys. There are also convergent boundaries, and these are when plates move together or towards each other, and this forms mountains. We also have the transform boundary, which is when plates move side by side or they slip past each other, and that's what causes earthquakes. So the image here is Figure 6 plate map. Earth scientists have identified the different tectonic plates, many of which are named for the continents they carry. The boundaries have been identified as convergent, divergent, or transform. Relative plate movements at some of the boundaries are indicated with red arrows. Using the map key as a reference, add the arrows that are missing in the circles provided. And your arrows should look like the arrows provided in this image. All right, before I move on to the divergent boundary here, we're going to do the reading check. So, which of the plates from the map would be a good starting point for a diagram that summarizes the different boundaries and why? So we're going to look at all of them and see what they look like. And we'll say that the Pacific plate, because it is large and has all three boundary types. Because it has the convergent in many locations, then there's divergent going on near the Caroline plate and the Pacific plate. And then on the other side, there's direction of plate movement, and there's also transform plate boundary. Over by the Antarctic plate and the North American plate, where it connects there on the left side of the map. But moving on now to the divergent boundary. Mid-ocean ridges and rift valleys are features of divergent boundaries. Some locations, molten material even flows through the gaps, creating new islands and volcanoes. We're going to do the map toolbox now. So Earth scientists measure plate movement by using the Global Positioning System, or GPS, of satellites. There are receivers anchored in Earth's surface that receive signals from the satellites and calculate their positions using the time it takes for signals to be received. Over time, changes in those signal times indicate plate movement. So, number 1, evidence from GPS readings suggests that the Mid-Atlantic Ridge spreads about 2.5 centimeters per year. How fast is the North American plate moving away from the ridge? Explain your answer. All right, so it is moving about 1.25 centimeters per year. The North American plate is on one side of the Mid-Atlantic Ridge. If the mid-ocean ridge spreads about 2.5 centimeters per year, that suggests that each side is moving away from the ridge at half that speed. So we took 2.5 centimeters and divided it by the number of sides of the ridge, which is 2. So 2.5 divided by 2, and that is how we ended up with 1.25 centimeters. All right, now 2, the Pacific plate moves to the northwest at an average rate of 10 centimeters per year. Hawaii is in the middle of the Pacific plate, 6,600 kilometers southeast of Japan, which is on the edge of several adjacent plates. If the Pacific plate continues to move at the same rate and in the same direction, when will Hawaii collide with Japan? Show your work. So, we have 6,600 kilometers, and that is equal to 660 million, It's a lot of zeros, and these zeros are so bad. Okay. A lot of zeros. Put in commas so I know I got them all there. Yes. So that's centimeters. All right, and then if it's moving at a rate of 10 centimeters per year, we will take our 660 million. So I'm going to do I'm using scientific notation just because it's easier. I don't know how familiar you are with scientific notation, but basically what I'm doing is 6.6 times 10, and that just moves the decimal place over. So let's count how many. 1, 2, 3, 4, 5, 6, 7, 8. So 6.6 times 10 to the 8th. And we're going to divide this number, which is 660 million. Divide that by the 10 centimeters per year. And then that is going to give us 66 million years. All right, moving on to a different form of boundaries, we have our convergent boundaries. This is where plates move toward each other and collide. And this is how the Himalayas were formed and how they're still being pushed up. So subduction occurs when plates are different densities. So for example, when the oceanic plate collides with a continental plate, the oceanic plates are denser and therefore will subduct. Sub meaning go under, so sub means under, and duct is movement. So subduct is going to go under, and the oceanic plate will go under the continental plate because the continental plate is less dense. And then up on top in the landform, that's how the mountains are going to form, because it's going to push that continental crust up to form the mountains. Okay, transform boundaries. This is when plates slide past one another, and earthquakes occur here on faults called transform faults. So when enough stress builds up, the fault ruptures and then an earthquake occurs. So here we have figure 9 on page 116, and that's the types of plate boundaries. The 3 types of plate boundaries are modeled here. Label each illustration with the term that describes the boundary. So this first one, they're pulling away, and that is our divergent boundary. I'm only going to write DIV. You guys should write divergent. Here they're being pushed together, con meaning with, so with together. This is our convergent. I'm only writing con. You guys should write convergent. And then trans means across. So these are going across, or they're going next to each other, and they're passing by each other. So that is the transformation, or transform, sorry, boundary. So I'm just going to write trans. Here, you should write transform boundary. Now we're going to go ahead and do the lesson, or the reading check. Sorry, I'm getting ahead of myself. What happens at divergent, convergent, and transform boundaries? So at a divergent boundary, plates move apart, and that causes things like ridges. Plates come together and collide at convergent boundaries, which causes mountains to form. Plates move past each other at transform boundaries, and that causes earthquakes. The divergent boundaries can also cause things like volcanoes to form new lands, etc. All right, so that finishes lesson 2. So we'll go ahead and do the lesson 2 check. At what type of plate boundary would you find a rift valley that is growing wider? And a rift occurs when you pull apart. So that is a divergent. 2, describe what is going on in this diagram. All right, and here we have 2 plates that are pushing together, and then the one is the less dense is going to go on top of the more dense plate. So 2 plates are converging at a convergent boundary. One plate is diving under the other in a process called subduction. The other plate's edge is being nudged upward, which creates mountains. Moving to 3. What other surface feature that is not shown in the diagram could be produced as a result of the process shown? And that would be volcanic mountains. It takes 100,000 years for a plate to move about 2 kilometers. What is the plate's rate of motion in centimeters per year? So in order to do that, we've got to change kilometers to centimeters. So to get kilometers to meters first, we have to move 1, 2, 3. That's at meters. And then from meters to centimeters, we move an additional 2, right? So we're adding 2 more here. All right. And 1, 2, 3, 4, 5. Yeah, so 200,000 centimeters. So 200,000 centimeters divided by 100,000 years is going to equal 2 centimeters per year. What does the theory of plate tectonics have that Wegener's hypothesis of continental drift did not have? The theory has an explanation for why and how the continents move. They're part of plates that move across Earth, carried by mantle convection currents. Wegener's hypothesis didn't have a reasonable explanation for how the continents moved.